In this video, I'm going to demonstrate how to calculate an electric potential for some extended object using an integral. Alright, so in particular, what I want to do is I want to find the electric potential due to a disk. So we're going to be interested in some spot that's a distance z away from the disk. And I want to find what that is. Okay, so what do we know? Well, we're going to know the radius of the disk, which I'll call capital R. We're going to know the charge of the disk, which I'll call Q. And we'll know the distance z from the disk. Also, when I calculate this, I'm going to assume that we already know the potential from a ring. I had you as an assignment calculate the electric field from a ring, and calculating the potential from a ring is even easier. What that is we get the potential from a ring is equal to K times the charge of the ring over the square root of R squared plus Z squared in this case. So essentially just the distance to the ring, where capital R is now the radius of the ring rather than the radius of the disk. Okay, so what I want to do then is I want to draw a careful picture, and I want to split the diagram into rings since I know the potential for each ring. Okay, so I'm going to draw this much larger now. Like this. So we know the radius, R. We know the distance away from the center of the ring, Z. And what I'm going to do is I'm going to split the ring, or split the disk into rings, I should say. So a narrow ring like this. And the radius of that ring I'll call little r, and the thickness of the ring I'm going to call dr, like that. Alright, another distance that I'm going to need here is the distance of this point from the ring, which I can calculate easily enough. And I think that is about it. So I don't need any other quantities. So I'll just call this cursive r, and we won't need it for very long, so it's okay that it has kind of a weird variable. Okay, so the idea here is that the potential from the disk is going to be the integral of the potential from a ring. Okay, so that's how we want to approach this. Alright, so what was the potential from the ring? So dV, which is the potential from the ring, is going to be equal to, well, we have an expression for that, K times dq, which is the charge of the ring, over square root of now little r squared, because the ring has a radius little r, plus z squared. Okay? And so I need to then come up with an expression for dq. And this is going to be a little bit tricky because the amount of charge on that ring depends on its radius. That will not be constant as we change r. So the way I want to think about this is that the charge on that ring as a fraction of the total charge is going to be equal to the area of that ring, dA, over the total area of the whole disk. Okay, so if 1% of the charge is on a small ring, then that's because it has 1% of the area. Alright, so what is the formula for the area of the whole disk? Well, that's just going to be pi times capital R squared. That's pretty easy. The area for the ring is a little tricky. So what I want you to imagine is that you cut through the ring like this. So here's my scissors, like that. So I cut the ring, and then I'm going to just stretch it out into a rectangle. So when I do that, I'm going to have this part, let's see, so I'm going to stretch it into this long, skinny rectangle. where the width of that is going to be 2 pi r, the circumference, and the thickness is going to be dr. Okay. You could actually find this in a more rigorous way, so you could name the inner radius and the outer radius and then take a limit as the two become equal in size, but I think that is way more work than you need to put into it. Just treat it as approximately a rectangle. The thinner the ring is, the closer that'll be to exact. So when we do the integral, we take it to infinitely thin, and then it's exact. Okay, so then this is going to be 2 pi r dr. All right, so then to get an expression for dq, I just solve. So dq is going to be 2 rq dr over r squared. So I've canceled the pi's in this. And then I can just plug that into my expression for the potential contribution from the ring. So dv ring is going to be equal to k times dq, which now I have an expression for. So 2q r dr over r squared. And we also have, in dv ring, this square root of r squared plus z squared. Okay, so what we want to do then is integrate to get v for the whole disk is equal to the integral of dv for the ring from r equals 0 to r equals capital R. Okay. And we have an expression for that, so let me just plug everything in. So I've got integral of 2k q over capital R squared r dr over the square root of r squared plus z squared from 0 to r. Okay, so at this point, that's basically it. All we have to do is do the integral, which is not actually all that difficult. So I'm just going to use a u substitution. So if I do u is equal to r squared plus z squared, and du is then going to be equal to 2r dr. Well, I actually have a 2r dr, so that works out really nicely. So then the potential for the disk is going to be all of the constants, so 2kq over capital R squared, integral of r equals 0 to r equals r of 1/2 du over square root of u. Okay, so I'm not going to update the limits because I'll just plug back in the original limits later. And so integrating this, what we end up with is 2kq over r squared square root of u. Okay, that works out really nicely. Again, evaluated from r equals 0 to r. And so I'm going to plug my expression for u back in. So 2kq over capital R squared times square root of my expression for u, which is r squared plus z squared, evaluated from 0 to r. So now if I plug that in, what I get is v disk is equal to 2kq over r squared square root of r squared plus z squared minus square root of z squared. All right? So this could be simplified in a number of ways. This looks slightly different from the expression in your book, but it is equivalent. One thing to notice is that this last bit is actually just absolute value of z. So this is a way that you can get an absolute value from doing calculation. In calculating the electric field before, we had to put in an absolute value explicitly. That's something that is talked about in the book. Here we can see that it just works. You calculate the potential and then the absolute value changes the direction of the electric field appropriately as you cross the plane of the disk. All right, so some things that I want you to notice from this derivation are, first of all, that up here when we were setting up the formula for the potential, we never had to worry about any trig functions because potential is a scalar. So the potential is a scalar, which means that we don't have to worry about the z component. We don't have to make a symmetry argument. We don't have to do any of those things. We can just write down an expression for the potential from each component and then add them up. Okay, so that makes things quite a bit nicer. Also, if you wanted to find the electric field, you still could, because we can just use the fact that Ez is equal to negative dv dz, and so you just take the derivative of this. And generally speaking, taking derivatives is way easier than doing integrals. So by doing an easier integral and then taking a derivative of it, that may often be a much easier way to find the electric field than trying to find the electric field directly in the first place.